I'm going to model some problem solving from chapter 2, our one-dimensional kinematics. And we're going to be doing problems 18, 27, 31, and 39. Each has a slightly different flavor or theme. And I just wanted to model what these should look like. So 18. An object moves along the x-axis according to the equation up, and I'm given an equation, so I'm going to write down that equation. 3t squared minus 2t plus 3 meters. Now, it's just something about this book, about the way that it does things. When it gives you coefficients like this, the coefficients are such that when you plug in the right units here, you end up with those units. So here, the implied units on the 3 here are going to be meters per second squared, because when I plug in seconds here and square them, I would want to get meters at the end. And so that is totally acceptable in terms of the way that we're doing this. So we're going to have units on first plugin and then units on answers and not units in the intervening work. Oftentimes it's very awkward to work with equations with the units around, and that's fine. So A, determine the average speed between t equals 2 seconds and t equals 3 seconds. Well, in order to know the average speed, what we have to know is what the position at the end of 2 seconds is and the position at the end of 3 seconds, so that we can figure that out. So we know what the displacement during that interval is, and then we'll use that to figure out the distance it travels. So here, all we would do is plug this into our calculator. I'll just show the plug-in, because that's what we should do, right? And there we go. And I can have that. So I can do this in my head. 412 minus 4 plus 3, so that is 8, 3, 11 meters and 3 seconds. So it's 3 seconds squared minus 2 times 3 seconds plus 3, and that gives us 927 minus 9 plus 3, or 30 minus 9, which is 21 meters. Therefore, it's not going to turn around in between those, so therefore the displacement here, delta x, is x at 3 seconds minus x at 2 seconds, which is going to equal 21 meters minus 11 meters, which is 10 meters. There we go. And that's going to be our distance then as well. So our displacement is 10 meters. The distance, delta x, the magnitude of, is 10 meters as well. Technically, the displacement is 10 meters forwards, but there you go. So if I want to know what the average speed is, then the average speed in that interval is total distance over total time. And so that's going to be 10 meters, 1 second. And there we go. I've got 10 meters per second. Okay, look at all the space. Look how it's beautifully organized. There's no questions about the progression of the work. It's not a little bit of work over here, a little bit of work over here, a little bit of work over here. It is an even progression downwards towards the answer. Okay. Then I want to know the instantaneous speeds at those times. Well, the instantaneous speeds, I need to know the magnitudes of the instantaneous velocities then. So I need to find the velocity. Easy enough. We know that the velocity is the derivative of the position function. And by the way, folks, that's my equation, right? We always want to write our equation of what we're doing. That's sufficient. You no longer have to do the sum rule or anything, just do the derivative. I don't care. 6t minus 2, and we know this comes out in meters per seconds. And I'm done, right? We're not going to belabor the point. That's my equation. There's my work. So the velocity at t equals 2 seconds is going to be 6 times 2 seconds minus 2, or we'll go 10 meters per second. And then v at 3 seconds is 6 times 3 seconds minus 2, and that's going to give us 16 meters per second. And there are our two answers there for what it wants the instantaneous speeds at those positions. Technically, that's forward and forward, but I just want the speed, so just the magnitudes thereof. So the next thing I want to know is the average acceleration between, well, we know that the average acceleration is just going to be v final minus v initial over the time period. We'll say just the delta t in this case. So in the time period 2 to 3 seconds, so that's using our stuff from before, 16 meters per second minus 10 meters per second, all over 3 seconds minus 2 seconds, because that's the interval. And there we go. I've got 6 over 1 seconds, or 6 meters per second. and that's my average acceleration. And then d, I want the instantaneous acceleration, so I'm going to go back and do a is equal to dv dt, and once again, I just get 6 meters per second squared. Here, the average acceleration is the same thing as the instantaneous acceleration at each point because it is a constant acceleration. I should have known that because if I have a position function of order 2, that means I'm going to have a polynomial as an expression. There's always going to be a constant acceleration. So there we go. Awesome. So now we can move on to the next problem. The next problem we said was 27. So here we go. Problem 27. Oh, it's another equation problem. A particle is moving along the x-axis. Its position is given by the equation. Let's write it down. X is equal to 2.003t minus 4t squared. Once again, these constants were, rather the units are all worked out, so this comes out in meters. The book specifies that, okay? And the t's are in seconds. So this one's a little bit different because that other problem was just straight calculus. This says, determine the position the instant it changes direction. So what we have to do is turn the question that they're doing into an objective. Determine the position the instant it changes direction. So I'm going to turn that into determine the position, find x when v equals 0. Because we know it changes direction when it stops instantaneously and starts going in the opposite direction. So I took what the book said and turned it into my own equation, or my own objective. So this is going to have two parts. First, I want to find out where the velocity is equal to 0, and then I'm going to do the next part. So here, find when v is equal to 0. So I'm going to do v is equal to dx dt. Notice I have a little title here for what my subjective is, because what I want to do is narrate my problem solving. And that's 3 minus 8t. And then I'm going to set that equal to 0. So 0 is equal to 3 minus 8t. So t, this is happening at 0.375 seconds. Perfect. So that's the instant at which it turns around. And now I'm going to find x, or I'm going to say find x of 0.375 seconds. And that's the answer. So here, this is x at 0.375 seconds is equal to 2 plus 3 times 0.375 seconds minus 4 times 0.375 seconds quantity squared. I'll grab my calculator and go 3 divided by 8 and square that times 4. Okay, and then I'm going to subtract off 3 times 0.375. Okay, subtract off 2. And I get that this is occurring at plus 2.56 and some other things. So there we go. We're just going to keep things to 3 figures here, 4 if the problem has really precise numbers in it, but we're not really going to deal with that. So there we go. So that's the A part of this. But notice how it's laid out. I've created the physics question. I've created the sub-objectives, and then I've solved the sub-objectives showing all the work underneath. Next, the velocity when it returns to the position it had at t equals 0. All right, well, I don't know the position it had at t equals 0, so we want to, find v, find v when x equals x initial. Okay, so first what we're going to do is find x initial, simple enough. We're going to do x at 0 seconds, and that's 2 plus 3 times 0 minus 4 times 0 squared. So that's clearly at 2 meters. And so now what we want to do is then we need to find the time. So find t when x equals 2 meters. So that's going to be using the position function. 2 meters is equal to 2 plus 3t minus 4t squared. Subtract the 2 over, 0 is equal to, I can factor out a t, 3 minus 4t, and that's going to happen at t equals 0, as well as at, or at t equals 3/4 of a second. There we go. So those two. Now notice this is a quadratic. That means I need to report both answers. Even though I know one of them is 0, who cares? This is a math problem from here to here. So I need to report all solutions of the mathematical process. Then I reject that because obviously it's at 2 meters at the start because that's its initial position. So now what we want to do is find v of 0.75 seconds. Okay, and so we're going to plug that into the velocity function that we found before. So here is equal to 3 minus 8 times 0.75 seconds. And we find out then what we get here is -3 meters per second, which is actually not that surprising if we think about what we have here. Let's go back to the original function. That's a parabola, right? And if I were to plot that parabola, it's going to have a downwards concavity because of the negative. It's going to have an x-intercept at 2, right? If this is x and t, and so it's going to do something like that. We know that this turning point is at 0.375 seconds, and so it should make sense that there's some symmetry in the parabola that halfway, there you go, once again, 0.75 seconds. Okay, so of course, the slope of this thing is the velocity. So if we're talking about the symmetry of the parabola, the slope at the other point here is going to be the same magnitude, but the opposite direction, right? So that's why here, the initial velocity, if we look at this, if we evaluate v as 0, is 3. Oh, look, there's 3. Because this is our x is equal to xi plus vit plus 1/2 at squared equation. That's all that is. So 3 is the initial velocity. -4 is half the acceleration, so the acceleration of this thing must be -8. And that's what this graph is, right? So the graphical interpretation of the calculus that we did before yields the same solution. But look how pretty that solution is, right? We've labeled our sub-objectives and we've accomplished everything in toward. So there we go. Those are some calculus type problems. Let's move on to some word type problems. 31. A jet plane lands with a speed of 100 meters per second and can accelerate at a maximum rate of -5 meters per second, right, as it comes to rest. So what do I want to do here? Well, this is not that important for this problem, but I'm going to just draw a little sketch because I always like to draw a little sketch. So here's my plane landing, boom, right? And so that's going to be our first thing, if we can. We want to draw a sketch with these types of problems. The next thing on the sketch that I want to do is I want to impose directionality. I want to make a declaration of what is positive and negative. So impose directionality. But really, actually, let's kick it up a notch. Let's not just impose directionality. Let's impose a coordinate system. Because coordinate system has directionality implied, right? So I'm going to call this position here x equals 0, and I'm going to say that is forward is positive there, right? So that gives a lot of meaning to what we're talking about here. It gives us a way of talking about our problems and what we know and we don't know in a very clear way. The third step we don't have to do in this problem. I'm going to leave it blank for the moment. The fourth step, what we're going to do here is write our knowns. And I know this seems like overkill for this problem, and by now you've already looked at the problem, you probably already have your answers, but I don't care, because what I'm trying to do is illustrate a methodology that can be used to attack any sort of problem. Now I'm going to leave some space for some other words here, okay? So what do I know here? Well, I know a couple of things, right? So xi, xf, vi, vf, a, t. I'm just going to write out all the things I could possibly know because I want to kind of think of this in a very systematic way. And so I know that the second it lands, I've declared that to be x equals 0. And so from the statement of this problem, I already know that the jet plane lands with an initial velocity of positive 100 meters per second. Now, they already tell us that the acceleration is -5 meters per second. I'm never going to do that in problem solving. I'm going to tell you it slows down. And then you would have to know that the acceleration acts in the opposite direction as the initial velocity, because the only time you slow down is when the acceleration is opposite what the direction the velocity is. So they're being really nice by telling you that negative sign. I'm not going to, because they're implying a forwards equals positive, which is totally logical, but it's not required. And therefore we want to get used to not having these like remnants of Descartes infecting our brains and being able to apply to a problem what we want it to look like to make problem solving easier. Because you can make these choices, and oftentimes these choices make problems easier. And we know this thing comes to rest. Okay, so writing the knowns. 5. Oftentimes we have to decode the objective, right? This is what am I looking for? In the last problem, we had to actually write a statement of what the physics problem was that was being asked. It wasn't clear. That's what I mean by this. Oftentimes this is as simple as writing down what the unknowns are in a nice simple problem like this one. Like for example, here in part A, they're saying from the instant the plane touches the runway, what's the minimum time before it come to the rest? So I want to know what T final is here. T final when V equals 0. Done. Nice and simple. Oftentimes here in decoding the objective, I want to write sub-objectives. If my initial information doesn't give me enough information to find out what I want to actually find, I need to decode that into sub-objectives like I did here where I said, ooh, first find xi, then find this, then find that. So it's nice and clear to the reader exactly what it is that's going on. So write a sub-objectives. And then what we want to do then is write linking equations. Oftentimes these are our kinematic equations, or our v is equal to dx dt, a is equal to dv dt, or some sort of equation. This one is nice and simple. Looking at the things I know, the things I don't know, I want t. I'm just going to use the equation of motion. xf is equal to xi plus vit plus 1/2 at squared. Now, we didn't use xf before. Oh, actually, no, I want to know t. I don't have xf. Oh, that's a terrible equation to use. Oh, no, I did it wrong. No, actually, looking at the b part of the problem, that's the equation I'm going to need when I get to the b part of the problem. So I'm just going to relabel this as the b part of the problem. When you write an equation down and you figure out that you can't use it, oftentimes you're going to need it later. Don't cross it out. Just leave blank space underneath and find out how to do it another way. Like, for example, here, find t when v is final is equal to 0. I can just use vf is equal to vi plus at. And by the way, that's a critical problem-solving thing that I just did there. You have to let the problem speak to you. You write down an equation, and then you're like, no, that doesn't work. That doesn't mean erase it and get rid of it. In fact, we want to leave it alone and leave space underneath it, and then realize by looking at the equation and looking at my list, I'm like, I messed up. I need to do something else. And then do something else. But do it in another column next to it, or skip a lot of space and then do it below. Whatever it is, you got to let the problem speak to you. So here we go. 0 is equal to 100 meters per second plus a negative 5 meters per second t. We solve this, t is equal to 20 seconds. Now, of course, I can come over here. I'm just going to put that in another problem here, 20 seconds. They tell us here, what's the second part of the problem? Can this plane land on at a small tropical island support where the runway is 0.8 kilometers long? Oh, so yeah, I find x when v is equal to 0 as well, right? So in other words, I need this time. So let's use this time and find out what x final is. So x final equals x initial. That term goes to 0. And here's what we're going to do. We're going to zero out the term. And there we go. Now I've got 100 meters per second times 20 seconds plus 1/2 negative 5 meters per second squared, 20 seconds, 20 squared. So that's 2,000 minus, notice units on the first plugin. I dropped them here. What's that? 400, 200, 200 times 5. So that's 1,000. Right? I did that right. Yep, cool. And that tells us that at that acceleration, I would need 1,000 meters in order to do that. That's not the answer to the problem here. Ready, folks? Because xf is greater than 800 meters. Therefore, this cannot land on this island. I did an explicit comparison. You can't just say, well, it's obvious. No, your job as a a problem solver is to actually answer the question addressed in a clear and unambiguous way so the reader doesn't have to do any work. It is your job to do the work. By the way, obviously, step 7 is solve. Okay, so there we go. We're going to figure out what parts 3 and 4 are in this next part of the problem. We've got 39. Okay, 39. Boom, I've got a ball starting from rest and accelerating while moving down an inclined plane that's 99 meters long. Okay, it reaches the bottom, it rolls up another plane. Oof, okay, cool, so I've got that. Where after moving 15 meters, it comes to rest. So I've got a ball here, I've got 9 meters here, I've got 15 meters here, and I've got the ball comes to rest again here. Okay, well, what are we going to do? Well, same thing we did before. Okay, we're going to draw a picture. Did it. We're going to impose a coordinate system. Now, here's the weird thing, folks. There's no reason why we can't bend our axis here, right? Because it just makes life a lot easier here. So we're going to bend our axis, and we're going to say the axis is positive along that. And that's going to be an important thing that we're going to figure out that we can do. We can bend our axis around the path of motion of an object as long as it's not doing anything super freaky. So this is really not doing anything super freaky. So we've imposed a coordinate system. Next, step 3. Here's the thing, though. What we have to do for this problem is a very important step, and that is to partition the problem. Here, because the acceleration is going to be different in the two segments, I need to break up the problem into a part 1 and a part 2. So anytime the acceleration changes, but I have constant acceleration in segments, I want to break up the problem or partition the problem. Another time to partition the problem is if there's different phases of the problem. For example, we're going to start to do problems where we throw things upwards. So something throws up and it comes down. We might want to break that up into up and down. Or we might want to look at the total trip, right? So the important thing is before you write down knowns, we have to write down what the partition is, because each part of the partition is going to have a different set of knowns. So here we go. So for part 1 of the problem, and we want to name our parts. Here I'm going to do 1 and 2. It could be up and down, east and left, east and west, left and right, whatever the parts of our problem are. So here we go. So I'm going to write xi1, xf1, vi1, vf1, a1, t1, xi2, xf2, vi2, vf2, a2, t2. Okay, cool. So we know that the ball starts from rest, so that's here, that's 0, and accelerates at, so we know this is going to be a speeding up acceleration, so it's going to be, with our declaration there, a positive 5 meters per second, and it's 9 meters long. So the end of part 1, xf is 9 meters. All right. Then it reaches, the ball rolls up a plane where after moving 15 meters, so actually xi here is 9 meters, because along our axis it's moved 9, and here it's moved another 15 meters, so that's 24 meters. It comes to rest at that point, so vf here is 0. So that's what I've got. And so I want to know what's the speed of the ball at the bottom of the first, right? So in other words, this is my answer to part A. I want to know how long it takes to roll down the first plane. This is my answer to B. What's the acceleration along the second plane? So this is my C. And what's the speed of the ball 8 meters along the second plane? So I actually don't care about that 24. We're going to have another separate thing for that part of the problem. And so now I've set up this nice little space here where I'm going to do work for the first set of knowns here and the work for the second set of knowns there. And there we go. So here we have it. So I want to find, we actually know that I want to set up my coordinate system. That's going to be x equals 0, right? So I know xi, xf, vi, a, and I want to know vf and t. Well, we don't want to think actually of this thing as a sequence, right? It's not that you do A, then B, then C, then D, then whatever, but just a series of objectives. If I wanted to do part A first, I could, because there's an equation, the VF squared equation. But I could also do part B first because I have the equation of motion, right? So don't get locked into thinking there's only one way to solve a problem. Now, I will just do these in this sequence. VF1 squared is equal to VI1 squared plus 2A1 delta X1. So filling that in, that's what I'm looking for, VF1 squared. I know that VI1 is going to go to 0, and then this is 2 times A, which is 0.5 meters per second, and then this is 9 meters minus 0 meters, right? And so then VF1 is equal to, pop that into your calculator, 18, half of 18, so it's just square root of 9, so plus or minus, and we're taking the square root, gotta have a plus or minus, 3 meters per second. Looking at the declaration, it makes sense to reject the negative because we know it's going forwards along that axis, positive 3 meters per second. Boom, box it, nice and simple. Now, I ran out of room here because I wrote pretty big, so I'm just going to go down below because I want to preserve my columns. Because that is a nice thing to do. Now, I could use the equation of motion, or I could actually just use a simpler equation now. VF1 is equal to VI1 plus A1T1. I think that's a little bit simpler based on what I know. So this is 3 meters per second, positive. We know that goes to 0. This is 0.5 meters per second, T1. T1 is 6 seconds. And I'm going to pop this up here. And oftentimes, I'll do that in a separate color so that I know the stuff that I had versus the stuff that was given at the end of the problem. It's really obvious to any reader. Now, how do I go into the second part of the partition? I know that there's links between the parts of the partition. The final velocity of the first part, by definition, has to be the initial velocity of the second part. And so there we go. So looking at this, I have VF2, VI2x, and I need A. This is clearly screaming for me to use the maximum height equation. So VF2 squared is equal to VI2 squared. I probably should have switched back to black, 2A2 delta x2. Okay, so here we go. We know that that is going to go to 0. This is 3 meters per second, quantity squared, plus 2 times, I don't know, A2, and then this is going to be 24 meters minus 9 meters. Okay, throw that in your calculator, 9/2 divided by 15, and we get that A is going to equal negative 0.3 meters per second. Boom, and that is the C part of this problem. I'll put this in here. And then the last thing just needs its own little section. I want to find in part 2 what is, and what is the question, what is V when delta x equals positive 8 meters per second, or 8 meters, that when you're that far up the second ramp. Okay, so this is looking like it's screaming to me. Notice I wrote a little sentence what my objective is. So VF in this part, and we can call this, I don't know, well, just it's within the 2's here. VF squared is equal to VI for part 2 squared plus 2 times A for part 2, and then delta x for this new delta x. So VF squared is equal to VI, which is 3 meters per second squared, plus 2 times negative 0.3 meters per second, and then this is 8 meters. So plugging that in, I've got a 0.3 times 2 times 8. Okay, whoops. 8, I'm trying to move too quickly here. Okay, great. And then 9, and then square root of 4.2, right? And I've got VF is equal to plus or minus, reject the minus because we know this thing is going up the incline, and this is 2.05 meters per second. That makes sense because it's less than 3, and it's greater than 0. It's going in the right direction, and there you have it, right? And so, going back to our methodology, sketch, impose a coordinate system, partition, write our knowns for each part of the partition, okay? Decode the objectives, write known unknowns sub-objectives if you need them, write linking equations and solve. Pretty much a lot of this unit is going to be dealing with the notion of partition. And that can be, by the way, partitions of space, like we've done here. We're going to see problems where there's partitions of time, like the object is doing one thing in one segment of time, one thing in another segment of time. And another partition actually is if I have multiple objects moving, I'm going to want to write a partition by object. And then when they get really interesting, you can sometimes have multiple objects that each need their own partition. And so you can see how this is going to go, all right? And then it's about finding the links between the parts of the partition. So, welcome to problem 2, problem solving.